All right, so here we are with Chapter 3, Number 33 on projectile motion. So it starts on Apollo 14 mission to the moon. Astronaut Alan Shepard hit a golf ball with a golf club improvised from a tool. The freefall acceleration on the moon is 1/6 of his value of it is on the Earth. Suppose he hit the ball with a speed of 25 meters per second at an angle of 30 degrees. So part A asks how long was the ball in flight? B, how far did it travel? And C, ignoring air resistance, how much farther would it travel on the moon than on Earth? So first thing first, let's write down what we know. So the first thing they tell us is that the gravity on the moon is going to be 1/6 the gravity on Earth. So if we do 1/6 of negative 9.8, we get that it is 1.63 meters per second squared on the moon. The next thing we know is that V sub O for this golf ball that is hit is 25 meters per second, and it's hit at an angle of 30 degrees. So first thing we're going to attack, let's find that X component. So it's got to be 25 times a cosine of 30, and that'll give us 21.7 meters per second. And the Y component of the speed is going to be 25 sine of 30, which is 12.5 meters per second. So for part A, right, how long was it in flight? So what is our time? So if we look at this, we all we know for this the extra component is the speed. We don't know anything else in terms of the distance it travels, so it's not going to help us find the time. Right? When we deal with the X, we need to know 2 out of those 3. So we look at the Y component. Luckily for the Y component, we don't need to know as much. As long as we know the speed, right, and the gravity, something like that, we can usually find it pretty quickly. So to find that time, that distance, I'm going to go with Y equals Y sub O plus V sub O Y T plus 1/2 G T squared. Now, this is the big jump here, the big thinking is when it goes through its entire flight, this golf ball, it has to get to the end. And at the end, right, the height that it is at the final travel, right, is going to be 0 meters. It's going to be, right, here's our golf ball, and it gets hit. It's going to travel up here, and then it's going to land over here again at the same height. So we're going to have a spot here, right, when time is equal to 0, and then when time is equal to what we're supposed to find, where the height is going to be 0. So we're going to have these 2 spots, and we'll have to, again, work out which one exactly is the one that we're going to worry about. So Y sub O is going to be 0, starting right at the origin right there. Right, V sub O Y is 12.5. Right, the T we don't know, so we'll leave it there. And plus 1/2 negative 1.63, right, because that is our gravity on the moon, and then T squared. So if we look at this, we can factor out a T. So we get 0 equals T times 12.5 plus 1/2 negative 1.63 T, like this. And when we look at this, we can see that T has to be equal to 0, or this quantity right here has to be equal to 0. Well, we know that T, when it equals 0, is right at the very start. So we know that that time is not going to be helpful for us. So it's probably going to be this quantity right here that is going to give us the time that it is in flight. So if we say that 0 is equal to 12.5 minus 0.815 T, and we solve for this T, we get that it is equal to 15.3 seconds. That sounds like it's a long time in flight, but we're dealing with on the moon, which has less gravity, so it's going to decelerate, change its acceleration very slowly. So here's our time for our flight. Part B then says to us, How far did it travel? So what is the x? Well, now that we know the speed and we know the time, we can find that x. So x is going to be equal to x sub o plus v sub o x t plus 1/2 a t squared. So x sub o is going to be equal to 0, starting again at that origin, plus our 21.7, which is our x component of the speed. We know that it is going to travel for 15 seconds, and then the other one, this last term is going to be 0 again because our a, there is no acceleration in the horizontal component. And when we put that together, we find that it's going to travel 332 meters when we're on the moon. Okay, so it's pretty far for a golf ball to be hit. In part C is where we put everything together. All right, we change it up a little bit. We'll do this in blue. So part C asks, ignoring air resistance, how much farther would it travel on the moon than on Earth? So what we're going to do is we need to know how far it travels on Earth. And because of this gravity thing, right, the time is going to be different as well. So what we're asked to do is do this process all over again, but now for Earth's acceleration because of gravity. So y equals y sub o plus v sub o y t plus 1/2 g t squared. So 0, 12.5 t plus 1/2 negative 9.8 t squared. So everything else stays the same except for that 9.8. If we follow the same pattern as we did for this piece right over here, we end up finding that t is going to be equal to 2.55 seconds. We now take that information and find that new range, or x sub o plus v sub o x t plus 1/2 a t squared. So 0 plus, we're at 21.7 times 2.55 plus 0. And we find that x is now equal to, on Earth, 55.3 meters. So this is our Earth. Okay. And they would like to know, what is the difference? So the difference is going to be the range on the moon minus the range on the Earth, which is 332 minus 55.3. So the difference between them is about 277 meters. That is how much farther you will hit it on the moon when compared to Earth. So clearly gravity, or the acceleration because of gravity, plays a large part in how far something travels when it's in projectile motion. So there we go. That's chapter 3, number 33.